Hello viewers, welcome to my channel Maths with VTC. In this video class, we are going to see the sixth chapter, triangles. Actually, what we are going to study in this chapter, similar triangles. Let us recollect the definition of congruent triangles. You recall that two figures are said to be congruent if they have same shape and same size. But in this chapter, we are going to study about figures which have the same shape but not necessarily the same size. So when two figures having the same shape are called similar figures, not necessarily the same size. Let us see some examples for similar figures. You consider all these circles. All are circles, therefore they are same shape. But what about the radius? Radii differ. Therefore, circles are similar figures. Now you consider these four squares. Since all are squares, they are same in shape. But what about the sides? For each square, the side is different from the other. Therefore, the squares are similar figures. Look at these triangles. Obviously, all the triangles are of the same shape, but side it differs. In fact, they seem to be equilateral triangles, so all the sides are equal. But a triangle to triangle, the length of the side is different. Therefore, these triangles are also similar figures. Now see this picture, it is a different one. Three pictures of Taj Mahal. Same picture of different size. Therefore, these three pictures are similar. Three figures are similar. Okay. Now this is the definition of similar polygons. Two polygons of the same number of sides are said to be similar. Two conditions must be satisfied. Condition number one, their corresponding angles are equal. Condition number two, their corresponding sides are in the same ratio or in proportion. So two conditions have to be satisfied for similar polygons. Consider the quadrilateral ABCD. Angle A is 105 degree, angle B is 100 degree, angle C is 70 degree, and angle D is 85 degree. Sides are different. Now you look at this quadrilateral PQRD. Angle P is 105 degree, angle Q is 100 degree, angle R is 70 degree, angle S is 85 degree. Therefore, the corresponding angles are equal. What about the sides? AB is 1.5 centimeter. What is PQ? The corresponding side 3 centimeter. What is the ratio? 1.5 divided by 3 is equal to 1 by 2. Now you look at BC, it is 2.5 centimeter. The corresponding side QR is 5 centimeter. So 2.5 divided by 5 is 1 by 2. Similarly, you can check all the sides are in proportion. Therefore, what you can say? These two quadrilaterals are similar. Consider this figure ABCD, which is a quadrilateral. In fact, it is a square. So all the angles are 90 degree and each side is equal to 3 centimeter. Now you look at this figure PQRS. This is also a quadrilateral. All the angles are 90 degree. Therefore, what you can say, the corresponding angles are equal. But what about the sides? AB is 3 centimeter, PQ is 3.5 centimeter. BC is 3 centimeter, QR is also 3 centimeter. Therefore, definitely the sides are not in proportion. Therefore, what you can say, these two quadrilaterals are not similar. Look at this quadrilateral ABCD. In fact, it is a square. So, all the angles are equal to 90 degree and each side is 2.1 centimeter. Consider this quadrilateral PQRS. All the sides are equal to 4.2 centimeter. Therefore, the ratio of the corresponding sides is equal. 2.1 divided by 4.2 is equal to 1 by 2. But what about the angles? In the first figure, all the angles are is equal to 90 degree, but in the second figure, it is not so. Therefore, the first condition is not satisfied. Therefore, what we can say, these two quadrilaterals are not similar. Thus, Either of the above two conditions, 1 and 2 of similarity of two polygons is not sufficient for them to be similar. Just one condition is not enough. Both the conditions must be satisfied in order to say that the figures are similar, the polygons are similar. Now exercise 6.1. Fill in the blanks using the correct word given in brackets. All circles are congruent, similar. Which is the correct word? Congruent or similar? All circles are similar because they differ only in size. Shape is same. Okay. Therefore, the answer is similar. Second question. All squares are of same shape, but the size depends upon the length of the side. Therefore, all squares are similar. All triangles are similar. So the statement is all triangles are similar. In that case, the triangles are isosceles or equilateral. Which is the correct answer? Isosceles triangles, only two sides are equal. But the third side, when you take two isosceles triangle, the two sides may be in same proportion. But the third side need not be in same proportion. Therefore, the answer is equilateral. So all triangles are similar. That means they are equilateral. Two polygons of the same number of sides are similar if their corresponding angles are dash and their corresponding sides are dash. Equal, proportional. So for the first answer is equal, for the second answer is proportional. Okay. Now second question. Give two different examples of pair of similar figures, non-similar figures. So let us consider similar figures. You consider these two circles. Obviously they are of same shape, but radius differs. Therefore, these two circles are similar figures. Consider these two triangles. Obviously both are equilateral triangles, but sides, length of the side differs. Therefore, they are similar triangles. Now you consider these two figures. First one is a square, the second one is rectangle. Therefore, angles may be same. But what about the second condition? The corresponding sides are not in proportion. Therefore, these two figures are not similar. Consider another example. It is a rhombus. This is a trapezium. Obviously, both the conditions are violated. Therefore, these two are also non-similar figures. Third question. State whether the following quadrilaterals are similar or not. P, Q, R, S. It seems to be a rhombus. Each side is equal to 1.5 centimeter. You consider this quadrilateral ABCD. It is a square. So each side is 3 centimeter. Therefore, the corresponding sides are in proportion. Same ratio. 1.5 divided by 3 is equal to 1 by 2. But what about the angles? Definitely the corresponding angles are not equal. Therefore, these two quadrilaterals are not similar because the corresponding angles are not equal. So that is the answer. Now, similarity of triangles. So far we discussed the similarity of polygons. Now we restrict ourselves only to triangles. Similarity of triangles. So the same condition we apply here. Two triangles are said to be similar if number one, their corresponding angles are equal, and number two, their corresponding sides are in the same ratio or in same proportion. So the same definition is mentioned here for triangles also. Now, this is an important point. If corresponding angles of two triangles are equal, then they are known as equiangular triangles. So, two triangles are given, the corresponding angles are equal. Therefore, you can say these two triangles are equiangular triangles. Now, this is an important result. A famous Greek mathematician Thales found a truth. What it was? The ratio of any two corresponding sides in two equiangular triangles is always the same. Therefore, as far as triangles are concerned, you can eliminate the second condition. That is what Thales found. So the ratio of any two corresponding sides in two equiangular triangles is always the same. So that is the significance of triangles. Now one activity. Draw any angle XAY and on its one arm AX, mark points P, Q, D, R and B such that AP is equal to PQ is equal to QD is equal to DR is equal to RB. So all these distances are equal. Now through B, draw any line intersecting arm AY at C. Also through the point D, draw a line parallel to BC to intersect AC at E. So first you marked P, Q, D, R, B, the points in such a way that AP is equal to PQ is equal to QD is equal to DR is equal to RB. And you draw a straight line from B to AY which touches at C. Next you draw another line from D to AY parallel to BC to meet at E. Now, what is AD by DB? AD is 3 units, DB is 2 units. Therefore, obviously, AD by DB is equal to 3 by 2. Measure AE and EC. What can you say about AE divided by EC? You might have guessed correctly. AE by EC is also equal to 3 by 2. So that is the property of triangles. Thus, you can see that in triangle ABC, DE is parallel to BC and AD divided by DB is equal to AE divided by EC. Now, we put this result in the form of a theorem. Theorem 6.1. If a line is drawn parallel to one side of a triangle to intersect the other two sides in distinct points, the other two sides are divided in the same ratio. It is a very interesting result. Now let us see the proof. We are given a triangle ABC in which a line parallel to that side BC intersects other two sides AB and AC at D and E respectively. You look at this figure. ABC is a given triangle and DE is drawn parallel to BC. D is a point on AB, E is a point on AC. Now, we have to prove that AD divided by DB is equal to AE divided by EC. How to prove it? To prove that result, let us join BE and CD and then draw DM perpendicular to AC and EN perpendicular to AB. Now you remember the formula for area of a triangle. What is the formula? Half into base into height. That is the area of a triangle. Area of a triangle is equal to half into base into height. Now I am going to apply that formula for the triangle ADE. I have taken AD as the base. Therefore, what is height? EN is the height. Therefore, area is half AD into EN. So, area of ADE is equal to half AD into EN. Similarly, area of BDE. When you take BD as base, here also the height is EN. Therefore, area of BDE is equal to half into DB into EN. Area of ADE is equal to half into AE into DM because AE is base and DM is the height. And the area of DEC is equal to half into EC into DM because EC is the base and DM is the height. So you have to be careful which triangles are to be considered for finding areas. Remember, we have to prove that AD divided by DB is equal to AE divided by EC. So I want these lengths in the formula. Okay. That's why I found the area of triangles. Therefore, area of ADE divided by area of BDE is equal to half into AD into EN divided by half into DB into EN, which is equal to AD divided by DB. Similarly, area of ADE divided by area of DEC is equal to AE divided by EC. So, these two results we have derived. Note that triangle BDE and triangle DEC are on the same base DE and between the same parallels BC and DE. Therefore, base will be same, height also will be same. Therefore, area must be same for these two triangles. Therefore, area of BDE is equal to area of DEC. You call this as equation number 3. Therefore, from 1, 2 and 3, we come to the conclusion that AD divided by DB is equal to AE divided by EC, which is a wonderful result in triangle. So, you have to remember this. You understand the concept and remember the result. Now, theorem 6.2. If a line divides any two sides of a triangle in the same ratio, then the line is parallel to the third side. It is exactly the converse of the previous theorem. So you draw a line which divides the sides in same ratio and then you have to prove that it is parallel to the third side. So this theorem can be proved by taking a line DE such that AD divided by DB is equal to AE divided by EC and assuming that DE is not parallel to BC. You see this figure. ABC is the triangle, DE is the required line. So that AD divided by DB is equal to AE divided by EC. This is given. Now we have to prove that DE is parallel. But I suppose that DE is not parallel. So what I am going to do, I draw a line which is parallel to BC from D to AC. Let it meet AC at E dash. If DE is not parallel to BC, draw a line DE dash parallel to BC. So AD divided by DB is equal to AE dash divided by E dash C. This is by theorem 6.1. Therefore, AE divided by EC is equal to AE dash divided by E dash C because we are given AD by DB is equal to AE by EC. Adding 1 to both sides of the above, we get EC is equal to E dash C. Thus, E and E dash coincide. That means E is equal to E dash. That means what? DE is parallel to BC. Therefore, this is just converse of theorem 6.1. Let us see one example. If a line intersects sides AB and AC of a triangle ABC at D and E respectively and is parallel to BC, prove that AD divided by AB is equal to AE divided by AC. You see this figure. So ABC is a triangle, DE is parallel to BC. By theorem 6.1, we know that AD divided by DB is equal to AE divided by EC. Or the reciprocal. DB by AD is equal to EC by AE. Now, you add 1 both sides. So, what will you get? DB plus AD divided by AD is equal to EC plus AE divided by AE. But DB plus AD is nothing but AB and EC plus AE is nothing but AC. Therefore, AB divided by AD is equal to AC divided by AE. When you find the reciprocal, you get AD divided by AB is equal to AE divided by AC. Example 2. ABCD is a trapezium with AB is parallel to DC. E and F are points on non-parallel sides AD and BC respectively such that EF is parallel to AB. Show that AE divided by ED is equal to BF divided by FC. Let us draw this diagram. So ABCD is the trapezium. So AB and DC are parallel sides. Now EF is drawn in such a way that EF is parallel to AB or parallel to DC. Now you have to prove that AE divided by ED is equal to BF divided by FC. So in order to prove the result, let us join A and C so that this line intersects EF at G. AB is parallel to DC and EF is parallel to AB. So EF is parallel to DC. Now we can apply theorem 6.1 to the triangle ADC. EG is parallel to DC. Therefore, AE divided by ED is equal to AG divided by GC. You call this as equation 1. Similarly, in triangle ACB, CG divided by GA is equal to CF divided by FB. You call this as 2, equation 2. Find the reciprocal both sides. AG divided by GC which is equal to BF divided by FC. You call this equation as 2. Therefore, from 1 and 2, AE divided by ED is equal to BF divided by FC. Now, example 3. In figure, PS divided by SQ is equal to PT divided by TR and angle PST is equal to angle PRQ. Prove that PQR is an isosceles triangle. To look at this figure, PQR, PS by SQ is equal to PT by TR and angle PST is equal to angle PRQ. We have to prove that PQR is an isosceles triangle. To prove PQR is an isosceles triangle, we have to prove that two of its sides are equal. Solution. It is given that PS divided by SQ is equal to PT divided by TR. Therefore, ST is parallel to QR. Therefore, angle PST is equal to angle PQR because they are corresponding angles. Also, it is given that angle PST is equal to angle PRQ. Therefore, by 1 and 2, angle PQR is equal to angle PRQ. Therefore, PQ is equal to PR. Why? Sides opposite to the equal angles. Therefore, they must be equal. Therefore, what is our conclusion? PQR is an isosceles triangle. Exercise 6.2. First problem. In figure 1 and 2, DE is parallel to BC. Find EC in 1 and AD in 2. So let us apply theorem 6.1 to the first triangle. DE is parallel to BC. Therefore, AD by DB is equal to AE divided by EC. Therefore, 1.5 divided by 3 is equal to 1 by EC. When you simplify, you get EC is equal to 2. Look at the second diagram. Here also you can apply theorem 6.1. So AD by DB is equal to AE by EC. AD by DB means AD divided by 7.2 which is equal to 1.8 divided by 5.4. When you simplify, you get AD as 1 by 3 into 7.2 which is equal to 2.4. Therefore, AD is equal to 2.4. Second problem. E and F are points on the sides PQ and PR respectively of a triangle PQR. For each of the following cases, state whether EF is parallel to QR. So we are going to apply theorem 6.1 for the following three cases. First, let us see the diagram. So PQR is a triangle. E is a point on the side PQ and F is a point on the side PR. So, if EF is parallel to QR, then the ratio PE divided by EQ must be equal to PF divided by FR. Let us consider the first case. PE divided by EQ is equal to 3.9 divided by 3, which is equal to 1.3. And PF divided by FR is equal to 3.6 divided by 2.4, which is equal to 1.5. Therefore, in the first case, EF is not parallel to QR. Now, let us go to the second case. PE is equal to 4, Q equal to 4.5, PF is equal to 8, and RF is equal to 9. When you find the ratio, both are equal to 8 by 9. Therefore, in this case, EF is parallel to QR. Third case, PQ is equal to 1.28, PF. Third case, when you find the ratio, PE divided by EQ is equal to 0.18 divided by 1.1, and PF by FR is also equal to 0.18 divided by 1.1. Therefore, in this case, EF is parallel to QR. Problem number 3. In the figure, if LM is parallel to CB and LN is parallel to CD, prove that AM divided by AB is equal to AN divided by AD. Solution. Consider the triangle ABC. We are given LM is parallel to CB. Therefore, when you apply theorem 6.1, you have AM divided by AB is equal to AL divided by AC. You call this as equation number 1. In the triangle ADC, LN is parallel to CD. Therefore, again by applying theorem 6.1, you get AN divided by AD is equal to AL divided by AC. You call this as 2. From 1 and 2, we get AM divided by AB, which is equal to AN divided by AD, which is the result to be proved. Fourth problem. In the figure, DE is parallel to AC and DF is parallel to AE. Prove that BF divided by FE is equal to BE divided by EC. So you have to carefully see the triangles for which you can apply theorem 6.1. Okay. Consider the triangle ABC. Since DE is parallel to AC, we have BD divided by DA is equal to BE divided by EC. Now you consider the triangle ABE. So DF is parallel to AE. Therefore, we can write BD divided by DA is equal to BF divided by FE. You call this equation as 2. From 1 and 2, left hand sides are equal. Therefore, right hand side must be equal. That is, BF divided by FE is equal to BE divided by EC, which is the result to be proved. Question number 5. In the figure, DE is parallel to OQ and DF is parallel to OR. Show that EF is parallel to QR. Solution. Consider the triangle OPQ. Since DE is parallel to OQ, we have PE divided by EQ is equal to PD divided by DO. You call this as equation number 1. Consider the triangle OPR. Since DF is parallel to OR, we have PD divided by DO is equal to PF divided by FR, and you call this as equation number 2. Now, from equation 1 and 2, you get PE divided by EQ is equal to PF divided by FR. Now, when you apply theorem 6.2, you get EF is parallel to QR. So, it is very simple. Sixth problem. In the figure, A, B, C are points on OP, OQ and OR respectively such that AB is parallel to PQ and AC is parallel to PR. Show that BC is parallel to QR. Solution. Consider the triangle OPQ. Since AB is parallel to PQ, we have OA divided by AP is equal to OB divided by BQ. Just apply theorem 6.1. In the triangle OPR, since AC is parallel to PR, we have OA divided by AP is equal to OC divided by CR. You call this as equation 2. From equation 1 and 2, we get OB divided by PQ is equal to OC divided by CR. Therefore, when you apply theorem 6.2, you get BC is parallel to QR. Number 7. Using theorem 6.1, prove that a line drawn through the midpoint of one side of a triangle parallel to another side bisects the third side. Consider this triangle ABC. E be the midpoint of AB. Let EF be produced to meet AC at F, and EF is parallel to BC. Then by theorem 6.1, AE divided by EB is equal to AF divided by FC. Since AE is equal to EB, you get 1 is equal to AF divided by FC. That means AF is equal to FC. That means what? F bisects the third side AC. Eighth problem. Using theorem 6.2, prove that the line joining the midpoints of any two sides of a triangle is parallel to the third side. So ABC is the triangle, E is the midpoint of AB, F is the midpoint of AC, EF is the line. We have to show that it is parallel to BC. So clearly AE by EB is equal to 1 and AF by FC is also equal to 1 because they are equal parts. So AE by EB is equal to AF by FC. So by theorem 6.2, EF is parallel to BC. Ninth problem. ABCD is a trapezium in which AB is parallel to DC and its own diagonals intersect each other at the point O. Show that AO divided by BO is equal to CO divided by DO. To prove this result, from O, you draw a line OL to the side BC so that OL is parallel to DC. Now consider the triangle CAB. Since OL is parallel to AB, we have CO divided by OA is equal to CL divided by LB by theorem 6.1. You call this equation as 1. Consider the triangle BDC. Since OL is parallel to DC, we have OB divided by OD is equal to BL divided by LC. You call this as equation 2. The reciprocal of 1 gives OA divided by CO is equal to LB divided by CL. You call this as equation number 3. By 2 and 3, we have OB divided by OD is equal to OA divided by CO. Transposing the terms, we get AO divided by BO is equal to CO divided by DO. Hence the solution. 10th problem. The diagonals of a quadrilateral ABCD intersect each other at the point O such that AO divided by BO is equal to CO divided by DO. Show that ABCD is a trapezium. So this is the picture of the quadrilateral ABCD. AC and BD intersect at O. Solution. To prove that the quadrilateral ABCD is a trapezium, it is enough to prove that the opposite sides AB and CD are parallel. So what I am doing, I am drawing a line OL parallel to AB and let it meet BC at L. Consider the triangle CAB. Since OL is parallel to AB, we have CO divided by AO is equal to CL divided by LB. You call this equation as 1. Given AO divided by BO is equal to CO divided by DO. Therefore, CO divided by AO is equal to DO divided by BO. You call this as equation number 2. Using 2 in 1, we get CL divided by LB is equal to DO divided by BO. In triangle BCD, the above result gives us that OL is parallel to CD. Therefore, OL is parallel to AB and OL is parallel to DC, which means AB and DC are parallel. Therefore, ABCD is a trapezium. Thank you students for watching my video. Please don't forget to subscribe and pass this video link to your friends too. Thank you.